Hey, all. I had a couple of requests for some help on the problem solving lab on dispersion forces and boiling point. The biggest issue seems to be with how to construct a graph. So you'll notice in our data table, we have the molar mass or AMUs of methane through octane, and alongside it, the boiling points of methane through octane. We're looking to graph all of this data and then interpret it. Now, it has to be to scale to be meaningful. So let's take a few moments here and let's draw a proper graph, shall we? So in this case, the smallest mass, 16 atomic mass units, and the smallest boiling point is minus 161.48 degrees Celsius. On the other side, our largest mass is 114. Our largest boiling point is 125.7. So we're looking to construct a graph to show the relationships between these two quantities and infer from the graph how dispersions change with increasing molecular mass. First, we have to be able to draw our axes. So along our x-axis, our mass in atomic mass units. Now we need to start with the smallest value of 16, if you recall, and our largest value must be 114. All right, so we've got our axis all set up here. So starting with 0 AMUs, we're going up all the way to 140 AMUs. That should be sufficient to fit all of our data. And then every one of those small squares is equal to exactly 1 atomic mass unit. Now, let's go up the other side of the graph. Here, we want to start with a negative 161. We got to go up to 125.7. So final minus initial will give us our change. Let's punch that into a calculator. That's 287.18, or we'll say probably about 300 degrees. Now, if we go back to our graph, our current graph axis is 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. So we got 110 here coming up our axis. That's going to make things pretty tough to fit in 300. So we're going to have to make this to scale. It won't be 1-to-1. All right. And now we label the axis. So this here is our boiling point in degrees C. Let's put in our first data point. So our first data point is methane. So at 16 AMUs, it's negative 161.48. Before we do that, sorry, our scale. So for our first, we look for 16. So there's our first data point. So we've got 16 AMUs, negative 161.48 degrees C, or thereabouts. Our next, at 30 AMUs, negative 88.6. Our next point, at 44 AMUs, negative 42. At 58, we've got roughly 0. At 72, we've got 36 degrees C. At 86, we've got 68.73. At 100 AMUs, we've got 98.5. And at 114, we have 125.7. So there's all of our data points graphed. Now, if we're going to extrapolate and determine the boiling point of decane, so later on we're asked to solve for the boiling point of decane, we can do this one of a couple ways. One way is for us to draw what's called a line of best fit, where we interpret the trend and we extend the trend beyond to find out where decane would be. Now, we have to predict the atomic mass of decane, but it looks like it's off our graph. Let's take a look here. So one way we might read our graph is we might look where the atomic mass of 140 would fall along our line of best fit, and we can make our prediction. As it stands currently, my graph does not extend that far. This is an issue. But one thing we can do to solve this problem is by solving for the equation of this line, as it represents y equals mx plus b. Let's give that a try. (212.5 degrees C), I run 90 AMU. All right, so let's set this up. So if y is equal to mx plus b, that would mean that y is equal to 2.4x plus our y-intercept, which is, in this case, we have it as negative 175 degrees C. So to demonstrate how this might look, let's take a look at a random data point here. Let's pick this point. It's right here. So at 30 AMUs, the boiling point is roughly 100 degrees below zero. So if we have y is equal to 2.4 and our x value of 30 minus 175 degrees C is about minus 100 degrees C, which is what we see right here. So any x value, meaning any of our mass values down here, when we plug into this equation, we should be able to solve for its boiling point. Well, let's take a look. What was decane again? You might recall decane had an atomic mass of about 140 AMUs. So let's plug that into our equation. So y is equal to 2.4 times 140 AMUs minus 175 degrees C. If you recall 2.4, there was a unit for our slope. Got a little lazy there. Our unit was our rise in degrees C over our run AMUs. This was degrees C per AMU. That was the unit of our slope, which is why when we multiply by AMUs, we end up with degrees C. All right, let's punch it in. We get 161 degrees Celsius. Actual boiling point. Not a bad estimate. So not a bad estimate at all. So what we're looking for you to be able to do as a skill here is to be able to create a scale graph, plot data on your graph, draw a line, and make an estimate. Now you can make an estimate any number of ways. You could have this graph axis, the y-axis, go higher than 150. That way you can just draw a line all the way up to where 140 crosses. Just need to be able to kind of draw on a curved ruler, maybe a curved surface, extend that line, and find where this point intersects. Then all you would need to do is draw another line that comes over along the y-axis. That would be your boiling point. All right, probably a better way to draw our line of best fit is to focus on just the last 1, 2, 3, 4, 5 data points. All those seem to agree pretty closely with each other. It's a more linear relationship. If we include the first couple data points, it becomes a curve, and that's just kind of ugly to deal with. Let's keep the math simple, shall we? In this case, we want to determine our y equals mx plus b. So here we've got our run. So we've got 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 110, 120. So we have a 120 AMU run. Now, if we look at the rise, we got 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, about 105. Now, don't forget the scale, which is 2.5 degrees C for every square. So that would make it 262.5 degrees C. That's our rise. So if we were to do our rise over our run, which gives us our slope of 2.2. If we were to describe our equation of the line here, our y equals mx plus b, pull my monitor still while I try to write on it. We've got y equals our slope, which is 2.2 degrees C per AMU, times x plus b, which is negative 125 degrees C. So if we were to use this value, that's our slope. That's the atomic mass of decane. 183 degrees Celsius, which pretty darn close to decane, if I'm not mistaken. So depending on how good you are at drawing a graph, you can eventually set this up so that this graph or the line of this graph is perfectly represented mathematically. If you're better at drawing graphs and you y equals mx plus b, you think, oh, easy peasy, lemon squeezy, no problem. Give me something hard. Why not add an extra variable? Make it a polynomial. Make it exponential. Give it a try. You can definitely do different types of graphical analysis to be more precise here. But in this case, our estimate still works pretty good.